Hi guys, welcome to my talk. This is the lipid energy model, new insights and data on fasting and cell structure. My conflicts of interest, I do get membership and Patreon revenue through Cholesterol Code, and I am a partner and managing director for Own Your Labs. The lipid energy model in a nutshell is kind of my first section. It's a little bit more of a refresher, if you will, and it's pretty basic, but we are going to build on it from here. As you know, many going on a low carb diet observe their cholesterol levels rise. And through a series of experiments, myself and many others have helped find connections between metabolic changes and cholesterol levels. I have and continue to hypothesize these cholesterol levels are highly influenced by the trafficking of fat around the body and lipoproteins. So I like this little analogy. What can this bag teach us about fat storage? Well, obviously you're looking at a mesh bag full of golf balls. But what if you couldn't open or close this bag? But what if you could break the balls apart to small enough pieces to get through the mesh holes? Well, then you might know a thing or two about fat-based storage. And it all starts with triglycerides. Triglycerides are the storage form of fat-based fuel. It's commonly found in adipocytes and lipoproteins. And this big bulky molecule, it's great because it stays within membranes really well. Well, with the help of an enzyme, one in particular we'll be talking about here shortly, we can break these apart. And at that point, they can slip through the membranes relatively easily. And I want you to know these constituent components. They're very important to this story. Glycerol is one. It's the 3-carbon chain that connects the fatty acids together. It's very soluble in the bloodstream, and it's commonly used by the liver to generate glucose. And there's free fatty acids, and this is the free form of fat-based fuel. It's commonly found in the bloodstream, often carried by a very prominent protein known as albumin. And this small molecule can easily slip through membranes. And I want you to bear this in mind. These two categories, they convert back and forth to each other all the time. Triglycerides to glycerol and free fatty acids, usually through hydrolysis. And glycerol and free fatty acids getting converted back to triglycerides via reesterification. So if we go topside, and we're looking at this in the context of particularly going from, like, say, a mixed or carbohydrate-centric diet into either a low-carb diet or fasting in a healthy context, we'd hypothesize the following. Body fat is going to have a higher continual release of free fatty acids from adipocytes, the fat cells. And moreover, some of these free fatty acids, they're being taken up by the liver as well. This results in a higher liver production of ketone bodies, the process known as ketogenesis, which we love to talk about in the keto world. And this is kind of important because ketones can cross the blood-brain barrier, so we need this for brain activity. All of this, it's not controversial. It gets a little bit trickier next, though, because what we also propose is that a great deal of these fatty acids, they're being reesterified into triglycerides in the liver. And there's now a higher secretion of these triglycerides on board lipoproteins, particularly VLDL particles. This allows for a greater direct supply of VLDL to both adipose and non-adipose tissues. And here's the important part. There's now a higher turnover of VLDL in delivering these triglycerides to tissues. That, we posit, results in more LDL particles, and therefore more LDL cholesterol that's being detected in the bloodstream. This is controversial, and understandably so. There's a lot of spirited debate in and outside the low-carb community as to what this means and how this works. And really, this bottom half of the flowchart is pretty much where a lot of my research lies. But what I want to do now is I want to drill in deeper specifically on body fat. And not just body fat, but also cell membranes, because this is an important part of the story. So what you're looking at right now is adipose tissue, which is what science would call body fat. And these are made of adipocytes. Adipocytes are pretty interesting looking. They kind of look like an eyeball. The nucleus is actually hugged up all the way to the side of the cell wall. And it otherwise has many things in common with most cells. It's got a mitochondria, Golgi, etc. But as you can see, it's predominantly this fat reservoir that's about 95% triglycerides, about 5% other lipids. So clearly, its main job is to maintain and hold on to these triglycerides in its reservoir. Now, what you may have also seen is that the cell wall, particularly the cell wall of a adipocyte, goes by what we call the fluid mosaic model. And there's sort of these three different functions, but I don't want you to pay too much function to it right now. Just know that it's important for it to maintain that wall. And that wall, its predominant components are phospholipids and cholesterol. Let's start with phospholipids. Phospholipids have a hydrophilic head, which means which means hydro as in water and philic as in loving. But they have hydrophobic tails that are made of free fatty acids. I shouldn't say free fatty acids, they're technically esterified to the phosphate group. But basically, these fatty acids, they are water hating. Like lipids, they tend to point away from water, while the head points toward it. This, along with cholesterol, allows us to build this lipid layer into ways that we want. What's neat about phospholipids is because of the polar head, they point towards the aqueous environment. So if they're completely submerged, it's kind of neat. They kind of snap together with the polar heads facing outward and the lipid tails facing inward, creating a kind of lipid environment right here. So if we're looking at a cell, what we expect to see is this bilayer, this combination of these phospholipids pointing towards the opposing phospholipids, while their heads point towards the aqueous environment. Blood is an aqueous environment, it's water-based, and cytoplasm on the inside of the cell is also water-based. But when we compare that to a lipoprotein, it has a monolayer. It has a monolayer because while the blood can be water-based, what it's traveling in, the inside is a lipid core. So it doesn't need to be a bilayer, it can be a monolayer. So now when you see this 3D rendering, it's not gonna throw you off because you know now you're looking at a lipid core, which is going to have a lot of different lipids. We'll be talking a lot about triglycerides, but there are other kinds of lipids, including cholesterol, that can be found inside. And these phospholipids and free cholesterol on the outside. Now let's look at a little bit more complex model. What you're looking at now is the lipid bilayer of a cell at the bottom. And the outside of the cell being the bloodstream, the inside of the cell being the cytoplasm. So the top is the outside of the cell in the bloodstream, the bottom being the inside. And up top, what we're looking at is a gigantic lipoprotein called a chylomicron. It's bloated with triglycerides. And I know it's a chylomicron given its size relative to the lipid bilayer. It's docked through the process of apolipoproteins and a receptor. But we're not going to care that much about this. What we care about is this process. When it's docked at this receptor, it's engaging in something called hydrolysis, which we discussed up top. And that's providing lipids to the cell underneath. Well, now I want to put on I'm using this is going to date me a little bit, but have you ever watched those 3D movies from like the 80s or 90s where they have the 3D glasses and they put them on and like one pane will be red and one will be blue and it says now it's time to put on those glasses. Well, anyway, now it's time to put on our lipid glasses where we're going to be focusing in particular on triglycerides, which you should also see as basically either triglycerides or glycerol and free fatty acids, phospholipids, and cholesterol. Obviously, that's a major focus of this talk, and for good reason, because now we need to discuss what happens following this hydrolysis where it's providing all of these triglycerides on board. Well, now that there's less, what happens? Well, as this lipoprotein releases lipid cargo, it needs to get smaller. But how does it get smaller? Let me tell you how it doesn't get smaller. Monolayer tightens gaps between the phospholipids and cholesterol. No, that's not. You can't just squeeze the molecules together. No, what has to happen is you have to actually have the monolayer releasing phospholipids and cholesterol in order to remodel to a smaller size. That's very important to understand, because now when you're looking at this lipoprotein, you're seeing that these lipids are coming off. If this needs to shrink from releasing lipids and the adipocyte is taking them on, this needs to grow to take them into storage. So adipocytes necessarily, if they are going to take on more lipids, they will normally have to increase their bilayer capacity. So here's a big, powerful way it can accomplish that. Now we're looking at a model that includes lots of lipoproteins that are being tethered. But as you can see, that one in the middle, it's actually engaging in something called lipoprotein endocytosis. Endocytosis means that the cell is taking in something. In fact, it's usually invaginating it, like in the case with this lipoprotein. This is receptor-mediated endocytosis. And by completely taking up this lipoprotein, the cell can incorporate its phospholipids and cholesterol to the bilayer. After all, the lipoprotein is literally made up of the same phospholipids and free cholesterol that the bilayer makes use of. Thus, we're not just growing the contents of this container, we're growing the container itself. Now let's talk about lipoprotein lipase and HDL. This study is fantastic. I love it. It's an in vitro study, and it's very dated. It goes all the way back to 1978. And what they did is they were looking at HDL in these two different species, which we'll talk about here in a moment. But it's important to recognize where they're dividing them. HDL2 is this larger size. It includes the alpha 1 and alpha 2 types. And you'll see that HDL3 is the smaller size. And this is actually closer to how they start out. They start out as closer to like an A3 or an A4. So this is what they did. They put bloated VLDLs that were bloated with triglycerides, into a solution. And what they saw was that there was a substantial hydrolysis, over 80% of VLDL triglycerides that occurred during this 4-hour incubation with lipoprotein lipase. Approximately 45% of both the VLDL protein and phospholipid and 15 to 20% of the VLDL cholesterol disappeared during lipolysis. Meanwhile, they had in the same solution HDL, nascent HDL, that was very delipidated, did not have a lot of lipids on board. And they saw that there was a substantial change that occurred with these HDL3 alongside this lipolysis of the VLDL. During the 4-hour incubation period without the enzyme, no changes. But when the lipase was present, the HDL3 disappeared completely, and in the end, the incubation was replaced by a less dense lipoprotein, which exhibited the flotation characteristics of HDL2. So don't miss this part. During lipolysis, apoproteins, phospholipids, and cholesterol were transferred from VLDL to HDL3, resulting in a 50% increase of the total mass of the lipoprotein. So what's happening? This VLDL, it's hydrolyzing, it's shedding all of these lipids, becoming smaller. Meanwhile, this HDL is naturally accepting it, almost like a magnet. It's just picking up all of the lipids, including the proteins, and coming into the larger size, HDL2. All that's added here is lipoprotein lipase. So this isn't in vivo, this is in vitro. So there's no tissue engagement, there's no receptors, nothing. We actually see this with just the addition of the lipoprotein lipase. And this is what put lipoprotein lipase on my radar even more than usual. Because wait a sec, isn't lipoprotein lipase just provided as needed from cells? Like many I read in lipidology, the focus is predominantly on receptors, not so much on lipases. And let me tell you, there's a lot of receptors, a huge family of receptors. But even LPL isn't really discussed that much from a regulatory standpoint. So, like many, I presumed LPL was provided as needed. In other words, there is very little regulatory influence on its production and supply. And wrong. There's enormous regulation into the transcription, the translation, and activation of LPL. I'm kind of frustrated that I got a bit sidetracked from what really was the more interesting story, and that's exactly how LPL is regulated in particular. From this recent review, for example, adipose tissue LPL activity is high in fed animals and low when animals are fasted. But most studies have shown that the opposite is true in the heart and skeletal muscle. So this makes a lot of sense. In the fed state, lipoprotein lipase activity is going up. It's storage time. We're going to store a lot of the fat. But interestingly, it's not universal. This doesn't apply to the heart and skeletal muscle. LPL activity goes down, which makes a lot of sense because there's now going to be a greater availability of other substrates from what you're eating. And smartly, it reverses. In the fasted state, LPL activity goes down, therefore sparing more of those lipoprotein-derived triglycerides. And heart and skeletal muscle LPL activity increases. In fact, while we're on LPL and the heart, note that the heart is a major site of LPL synthesis, and fatty acids provide over 70% of the energy needs for cardiac muscle. Not surprisingly, cardiac muscle is the tissue with the greatest expression of lipoprotein lipase, and thus lipoprotein lipase is likely to be an important enzyme in cardiac lipid uptake and metabolism. Note this last sentence here. Neither non-esterified fatty acids, the free fatty acids, nor the compensatory increase in cardiac glucose metabolism can entirely replace the fatty acids not provided by LPL in the heart. To put it plainly, your heart doesn't just love fatty acids. Your heart loves fatty acids it's hydrolysizing off of lipoproteins in particular. So now let's bring it back to LPL and adipose. In mature adipocytes or adipose tissue, insulin not only increases the level of LPL mRNA, but also regulates LPL activity through both post-transcriptional and post-translational mechanisms. Glucose also increases adipose tissue LPL activity. The glucose stimulatory effect appears to be mostly through the glycosylation of LPL, which is essential for LPL catalytic activity and secretion. And glucose also stimulates LPL synthetic rate and potentiates the stimulatory effect of insulin. So a great way to grow your adipocytes is to get them a lot of insulin, a lot of glucose. Now, I love this study, and this is a table from it. It's fatty acid metabolism in adipose tissue, muscle, and liver. And I like it because it's a great kinetic study that really isolates down these two columns between adipose tissue, skeletal muscle in particular. And what you see is adipose tissue, if you were to just ask it, hey, where did you get most of your fat-based energy today? What were you filling your cytoplasm with for your triglycerides? Well, it's getting most of them direct from lipoproteins, LP being short for lipoproteins, so triglycerides off of lipoproteins. Meanwhile, what about skeletal muscle? Is it getting about the same amount? It's not. It's getting about a third, about 10 grams a day, compared to what it normally gets. What it's normally getting, 2/3, are non-esterified fatty acids. And where would it be getting non-esterified fatty acids? Well, likely from adipose tissue. And thus, the bottom line is adipose is the major consumer of triglycerides, onboard lipoproteins in the serum. And it seems to be providing a lot to skeletal muscle, which is why I really like this next slide a lot. It emphasizes triglyceride-rich lipoproteins. In adipose tissue, you can almost think the relationship is it's kind of the global distributor to adipose tissue. And you can think of the cells as getting a lot of its local distribution of fatty acids direct from adipose tissue, including to some degree some fatty acids that actually get re-esterified back into adipocytes. So let's take this into the context of the fed state versus the fasted state. If we're looking first at the fed state, what do we expect to be happening, particularly on a fat-adapted diet? We expect that we're going to be getting a lot of chylomicrons and VLDLs, which are bloated with triglycerides, providing, yes, some of these fatty acids to different tissues in need, but a lot of it is the repleting of adipose tissue. After all, we're in a state of abundance, in a predominantly fat storage mode. However, eventually we're going to fit over to the fasted state. And now we want to release more of these free fatty acids from adipose tissue to provide, as needed, to all of these different tissues. And VLDL will, to some degree, provide some as well. And depending on how low you are, or I should say how much you're fasted, some amount of triglycerides will be provided by VLDL, but nowhere close to where we would be in the fed state. And again, it kind of depends on the context. So let's put the glasses back on again. And let's really focus on these three elements. On ApoB lipoproteins, that includes VLDLs and LDLs and so forth, and high density lipoproteins, and their relationship with adipocytes, and in particular, this relationship with adipose LPL activity, lipoprotein lipase, as it plays into this. Well, we can speculate that if lipoprotein lipase activity is increased at adipocytes under healthy conditions, and all else being equal, we should generally see greater uptake of triglycerides from ApoB lipoproteins like chylomicrons and VLDL, higher turnover of VLDL triglycerides, which means more VLDL, phospholipids, and cholesterol transferred to HDL, right? So we're seeing LPL resulting in more of this going into the adipocyte, more of the cholesterol and phospholipids going into HDL particle species, and more remodeling of VLDL to LDL. But bear in mind also greater growth of adipocytes. This needs to grow. Therefore, it's going to require more endocytosis of lipoproteins like LDL. We can flip the script and you can imagine the same thing. So note, now adipocytes are releasing a lot of these free fatty acids. There's less free fatty acids coming in from ApoB lipoproteins, less of these phospholipids and cholesterol going over. So sure enough, less uptake of triglycerides from ApoB lipoproteins like chylomicrons and VLDL. Lower turnover of VLDL triglycerides means less VLDL phospholipids and cholesterol transferred to HDL. Less remodeling of VLDL to LDL, and reduced growth of adipocytes requires less endocytosis of lipoproteins like LDL, so more LDL would be left in the serum. And fortunately, I have a huge amount of experimental data to look at this against. In fact, let's just take a time trip back to my original LDL-C inversion as first presented in Breckenridge in 2017. Sure enough, would I think that this higher fat intake would result in marginally higher insulin and therefore greater adipose LPL activity? Yes. And therefore this drop in LDL-C I think is a combination of more of the LDL-C moving to the HDL species and more endocytosis of LDL particles. Likewise, I would expect the reverse, that if my fat-based diet is going down, we're going to see a reduction in adipose lipoprotein lipase activity, which could result in an increase in LDL cholesterol and LDL particle count. And this is what's great, is I actually presented this then, but didn't have as much opinion on what made this make sense. But now in this talk, you should hopefully understand the HDL-C cholesterol going up, I think, is a strong proxy for adipose lipoprotein lipase activity. So in these data points where I'm consuming a huge amount of fat and HDL seems to track with it, I think that's in large part for the same reason that LDL-C is not, that we're actually watching a lot more transference of those lipids to the other species. You may have known about this experiment from Keto Fest. Remember, on Friday, 7/14 of 2017, we had everyone be on a hypocaloric diet or just straight up fasting. Each of these dots represents the baseline for everybody on that Friday. We had quite a spectrum because this is LDL-C, the axes on one side. And you can see that almost everybody goes down, or more specifically of the 22, 19 had a decrease of between 5 and 38% of their LDL cholesterol, whereas 3 had an increase of between 1 and 2%, which is quite substantial. This is from my weight gain, weight loss experiment. You can see another inversion pattern between what's picked up by my cardio check LDL and my weight. And sure enough, at my peak, I was at 204 0.5 pounds. And at my nadir, I was 199.2. My bottom at LDL of 133 was just before I switched over to a ketogenic diet. So again, this whole section on the left side is when I was on a standard American diet, and I took all these metrics as I switched that off and started heading over to the ketogenic diet, where we see my LDL climb up to 228 at its peak. But if you invert this graph, so if we invert this axis on the left side, you can see how tight this inversion pattern is. The Pearson of negative 0.936, or to geek out and put it on a scatter plot, it's a R2 of 0.8481. That's extremely strong of LDL-C versus weight. Granted, this isn't a transient period, but it's very strong data. But the most robust data I have is from the replication experiment data, and we can look at it in light of this model. So I'm not going to go through all of the different aspects of this experiment. I'm just going to say the main thing to keep in mind is that the first 5 days were a maintenance phase. The second 5 days were a hypocaloric phase. And I took wide spectrum blood tests at the end of each of these phases. And then I switched from the hypocaloric phase over to a hypercaloric phase, high calories, for 5 days. Now my body weight for all phases are detailed over these two experiments. So bear in mind, version 1, this first column, this is referencing the experiment that I did identically from 2 years ago. Version 2 was from 6 months ago. Again, these experiments were identical in nature. And what we can see is in version 1 and version 2, I was indeed seemingly at baseline at my maintenance calories, pretty close to holding to my weight. I started at different weights in each one. I started at 196 pounds for version 1, which again was about 2 years ago. And obviously, if this is my maintenance level, it's precipitating down. But for my baseline for the second experiment, where I started 4 pounds lighter, I seem to be holding pretty well. Unsurprisingly, hypocaloric, I end up dropping weight. Also unsurprisingly, hypercaloric, I start gaining weight. Glucose, likewise, won't surprise anyone. At baseline, I seem to be steady. And then I start to drop at the hypocaloric, and then start to increase at the hypercaloric. Next, we have beta hydroxybutyrate, which of course are ketone bodies, and you can see it goes inversely with glucose. Baseline, I'm holding steady, but then at hypocaloric, it starts to climb substantially. Hypercaloric, it then drops. LDL cholesterol follows the inversion pattern. It generally goes up in both experiments and then generally drops in both experiments as I go hypercaloric. But now I want you to pay extra attention to HDL cholesterol. It goes in the opposite direction. As I go hypercaloric, it goes down and eventually even drops to its nadir on the morning of day 2, 38 in version 1, 46 in version 2, and note that it's all the way up to 65 and 64 just 5 days later. Triglycerides can be coupled with it. You see likewise a huge substantial spike that happens here. I'm definitely hypertriglyceridemic on that same morning of day 2 for both version 1 and version 2. Again, these are like a year and a half apart, by the way. So what do I think is happening? Well, taking it topside again, I think there's definitely more chylomicrons coming in because there's a greater consumption of more fat and glucose. Not a lot of glucose, but a little more glucose, certainly proportional to what I was eating before, which means greater insulin, higher leptin, and therefore a lower amount of lipolysis. And this in turn means greater energy competition between this state of change from release to storage. I'm predominantly releasing fatty acids, and now I'm going to storing them. And this is pretty profound when you think about it in this context. My glucose hardly changed when going from hypo to hyper. Not true with my triglycerides. Again, my triglycerides spiked substantially. So what do I think is going on? Well, I think it's Occam's razor. I think if this arrow, whatever this amount is for adipose LPL activity, this would be day 1. then I think this is closer to what day 2 and later looks like. A substantial increase. Because basically what I think, to keep it simple, is I think adipose lipoprotein lipase production, we have to produce this enzyme. It may need to catch up to its activity demand in this context. So think about it this way. My body fat for 5 days is getting the following signal. Hey, we're in a state of scarcity. And therefore, the proportionality of the enzymes, and really just about every protein, is probably going to be affixed to what that context is. And then all of a sudden I go from that to hypercaloric. Well, we have to get those proportions shifted. We have to get the transcription and the translation for everything associated with it. And that may not be truly overnight. But as I like to joke, it might be 2 overnight, because 48 hours later, now we're finally bringing it way back down, and we're now fully back into storage. Now let's look at the phase completion. So each completion of the 5 phases, I had wide spectrum blood work. So remember, here's a breakdown. Maintenance was roughly these calories with this breakdown of macronutrients. We have hormones that basically follow what we'd expect. Insulin, leptin, free T3, they all go down when I'm hypocaloric. They're all going up when I'm hypercaloric. Same thing with energy substrates. Glucose is generally going down when I'm hypocaloric, up when I'm hypercaloric, whereas the fatty acids, free fatty acids, triglycerides flip with it. But now of more interest, let's look at non-HDL cholesterol, because of course this is cholesterol that's going to be found on ApoB species of lipoproteins, and HDL cholesterol. And it's this perfect inverse pattern when going from maintenance to hypo to hyper. And same exact thing with ApoB versus ApoA1. This is a direct count of those apolipoproteins, which perfectly match between the cholesterol content. What's really great, though, is we also have, with Boston Heart, we have this cholesterol balance assay, and it's proved very powerful in looking at the model. So lathosterol and desmosterol are markers for cholesterol synthesis. If you look at total cholesterol, you can see that it follows the inversion pattern. As I go hypocaloric, it goes way up. As I go hypercaloric, it drops way down. So would we expect the synthesis to follow the same pattern? Actually, no. It's the opposite. At maintenance level, it's here, and it ends up dropping marginally. It goes down slightly. But when I go hypercaloric, both of these markers jump substantially. In the case of, for example, lathosterol, it's threefold. So even though the detected amount in the serum is higher, the production is lower, and vice versa, the detected amount goes down. So in spite of lower total and LDL cholesterol detected in the bloodstream, production of cholesterol has increased substantially, presumably, to meet trafficking and tissue demands. Obviously, as a major central part of this talk, I'm suggesting that one of those tissue demands in particular is adipose tissue. Boston Heart also has an HDL map. And now we get back to the real goods, where we can look at this HDL map. We can see that it divides out these different subtypes that I was talking about before. But note that, generally speaking, you want your alpha 1 and alpha 2 to show up as high. The higher the better. You want to get above this marker. But it works the opposite on the nascent. You don't want to have a whole lot of A3 and A4 detected in the blood, because that's associated with worse outcomes. Well, here are my numbers. We see the alpha 1, alpha 2, these are the bigger, alpha 3, alpha 4, and pre-beta. And I'm going to superimpose real quick this HDL2 species group and the HDL3 species group. And now look at what happened with the experiment. In the hypocaloric phase, we see that there is a decreased, or at least we assume there's a decreased adipose LPL activity. The hypothesis is LPL turnover should move less cholesterol and phospholipids to HDL lipoproteins. Thus, HDL species should get smaller as well. Is that what we see? We do. We see more of these in the HDL3 column relative to the maintenance level, and definitely relative to the hypercaloric level. But the same thing with the HDL2 species. This is when it's at its lowest, at 60 especially. Likewise, we see with the increased adipose LPL activity, we'd hypothesize it's the opposite, right? That there's more turnover, resulting in more cholesterol and phospholipids going to HDL lipoproteins. Thus, HDL species should get larger. This is the largest that we're seeing at 61.3, 74.8 in the HDL2 larger size. Less that's found in the A3, A4, and pre-beta relative to the other categories. So this perfectly fits the model as we've described it before. So let's revisit the triad for a second, because hopefully by now you can see why it is that I seem to keep revisiting just the basic lipid panel, and why I think it's so important more now than ever to look at the combination of high HDL cholesterol and low triglycerides with high LDL cholesterol. And don't get me wrong, even if you don't have high LDL cholesterol, it makes sense as to why high HDL cholesterol and low triglycerides can be so powerful in suggesting where your state of your existing lipid system lies. Because that's the power of looking at this against what was already here long before I got into this work, this phenotype known as atherogenic dyslipidemia. And bear in mind, these are part of the 5 criteria of metabolic syndrome: low HDL cholesterol and high triglycerides, and how this is almost the opposite of what we see with the lipid triad. I think that there's quite a lot that links metabolic disease, especially as it applies to cardiovascular disease. So with that, I want to set up this next section by talking about a brief history of the lipid hypothesis. This is doctors Michael S. Brown and Joseph L. Goldstein. They met in 1966, beginning an internship at Massachusetts General Hospital of Internal Medicine. They started a joint laboratory in 1972, and ultimately they would be awarded the 1985 Nobel Prize in Physiology or Medicine for the groundbreaking discovery of the LDL receptor. Their work is quite seminal. And see, they had a pivotal patient. When speaking of clinical duties early in their careers while at the NIH, Dr. Brown says, and there we saw a patient that actually determined the scientific course of the rest of our lives. This patient was a little girl with homozygous familial hypercholesterolemia. Note that her total cholesterol is 850, her LDL is 783, and it's heartbreaking, but she had an angina and presentable xanthomas at age 3, and she had her first heart attack at age 6. Goldstein says, this little girl had only an elevated LDL. She had no high blood pressure, she had no diabetes, she didn't smoke, she didn't have type A personality. Her only risk factor for having a heart attack at age 6 was this high level of LDL. So it's one of the best examples of a disease where we really know the cause. The cause of the disease is that this little girl has an increased level to her LDL. You may have seen this graph before. This is from low density lipoproteins cause atherosclerotic cardiovascular disease. This, I think, came out in 2017 from the EAS. And without question, I mean, we can superimpose it. Right up here is the LDL receptor for FH. This is one of the strongest, most powerful indicators from conventional medicine's perspective to demonstrate that LDL causes atherosclerosis. Same thing when you look at this one, which is eradicating the burden of atherosclerotic cardiovascular disease by lowering lipoprotein B lipoproteins earlier in life. This does a pretty good job of kind of putting it on a time scale, going from birth to age 80. The higher your LDL, the more you should observe a higher amount of atherosclerosis. And of course, this is FH. This is actually even at heterozygous FH levels at 390. It's still fairly high, but it suggests that you should be actually seeing an event and definitely a progression of plaque. So without question, if the higher LDL as a result from FH is the primary driver of atherosclerosis in the absence of other risk factors, it provides compelling evidence for the lipid hypothesis. There hasn't been any circumstance where one would have substantially higher total and LDL cholesterol without it resulting from genetic familial hypercholesterolemia. It just didn't happen until now. Thus, we bring you the lean mass hyperresponders study. And I have to pose this question: why are low-carb hyperresponders receiving so little research in lipidology, in spite of many years of reaching out to former lipidologists by yours truly? In the interest of expanding this research, progress has been slow to gather interest. And one possible reason for this reluctance is the extraordinary high levels of total and LDL cholesterol common within our community. And it's understandable, right? They're looking at Brown and Goldstein. They're looking at the foundation of the lipid hypothesis, and it's very compelling to, if you feel genetic FH is more than proof positive on its own, to suggest that causal nature. Well, of course, you've seen this slide, I'm sure, several times before. This really coming all the way back from 2017, with just some minor modifications. But basically, we have this phenotype. We have lean mass hyperresponders, which have that triad at extraordinary levels. And so we're putting together a study on lean mass hyperresponders. And as of now, over the last half year, actually I need to update the text on this. It's now been about a year and a half. We've raised almost $250,000 toward the study on lean mass hyperresponders. And we'll be capturing CTA scans at the beginning and at follow-up 1 year later, along with wide-spectrum blood testing. Our team includes, by the way, people of differing expectations for outcome. I love that, by the way, that we have conflicting hypotheses for the risk level. So it's really kind of come to a head in many respects. I feel like this study needed to happen before we could even unlock the amount of research that I think lean mass hyperresponders will bring us. I think this phenotype in particular, I think this triad will bring about new levels of data and understanding that we just didn't have access to before. I want to finish real quick by thanking all members and patrons that, there's just no way we could get this work done without them. And I want to thank you for watching this talk.